I want to tell you about a scream that took 1 billion years to arrive, and I still don't quite believe you're going to make me believe it. A very long time ago, so long ago that the Earth had only just cooled enough to hold an ocean, and there was nothing walking about on it clever enough to wonder about anything, two black holes far out in the dark finished a dance they had been losing for an age. They fell into each other, and the instant they touched, the crash flung a shudder out through the shape of space itself. A ripple in the fabric, racing away in every direction at the speed of light. That ripple travelled for 1 billion years. It crossed the whole gulf between the stars, while life on Earth crawled up out of the sea and learned to stand and build and ask questions. And then, one perfectly ordinary morning, not long ago at all, it washed over the Earth. It stretched you and me and everyone by less than the width of the tiny speck at the heart of an atom. And for the first time in the whole history of our kind, something we had built was listening, and we felt it go by.
We felt it go by. Yes, and I want you to sit with how outrageous that sentence is before we take a single step toward explaining it. Not, we saw a flash. Not, we caught some light of a distant fire. We felt the shape of space quiver, the ground of everything, the stage the whole universe stands upon. We felt the stage itself tremble. From a collision so far away, the word far quietly stops meaning anything. Think of everything you have ever touched. Every ocean, every mountain, every star you have ever looked up at. All of it sits inside that one fabric, resting on it, made of it. And for the space of a single morning, the fabric itself rang like struck crystal, and we happened to be quick enough and quiet enough and clever enough to catch the very last of the ringing. That morning is, to my mind, one of the great mornings in the story of our species, and it is the whole of tonight.
But you've handed me a paradox in the very first breath, and I can't walk past it. You said the ripple stretched me by less than the width of the thing at the middle of an atom. That is nothing. That is so far below nothing, I don't have a word small enough to reach it. Stretch a whole person by less than a piece of an atom. You'd have a better chance of noticing if I moved a single mountain the width of a whisper. So how does anybody feel a stretch that small? How is that not simply wishful thinking with very expensive equipment and a great deal of hope?
It's the best question you could ask, and we'll spend a good part of the night on it. Because the smallness is not a footnote. The smallness is the whole miracle. But not yet. First, I have to earn the ripple. Cast your mind back to where I left you last time, at the very edge of the dark.
The black holes. You left me falling into one. A charming way to end an evening, thank you for that. And right at the end you said a thing I've been turning over ever since. You said that when two of these monsters collide, they don't just merge and go quiet. You said they ring. Like a bell.
Like a bell. And I said it on purpose, because it's the door into everything tonight. Last time you learned that a black hole is a place where space-time is bent as far as bending will go. A pit with an edge you can fall clean through and never climb back out of. Tonight the question is simpler and stranger than any we've asked in this whole course. We know space-time can bend. We've spent 9 evenings watching it bend, around stars, around the Earth, all the way down to the throat of a black hole. So here it is, the whole night in one breath. If space-time can bend, can it shake?
Oh, that's a lovely question. The sort that sounds like nothing at a dinner table and turns out to be the loose thread the whole coat hangs from. Can it shake? Can the fabric wobble? And I already suspect it's going to cost me a night's sleep.
It may, and I'll not apologize. But to feel why the question makes sense, think about any bendy thing you've ever met. Press your hand flat into a mattress, you make a dent. Hold your hand still, and the dent sits there, patient, going nowhere.
And that's a star, isn't it? The picture you've drawn me all season. A heavy thing sitting in space, holding its dent open. The standing pit that keeps the planets wheeling round it year after year.
A star exactly, a hand pressed into the fabric, holding a steady dent. But now don't press. Slap the flat, calm surface of a still pond, hard, and snatch your hand away.
And it doesn't just dent, the dent runs. A ring goes racing out across the water, away from where my hand struck, spreading in a widening circle to the reeds at the edges.
The dent runs, and that is the whole of the difference. A star holds a steady dent forever, but jostle the fabric hard enough and the disturbance won't sit still. It picks up its feet and travels, spreading outward, carrying the news of the jostling away. Einstein saw that the moment he had his finished equation in his hands. He'd built a theory in which space-time bends and flexes and answers back. And a thing that can flex
Can carry a wave, of course it can. And he saw all that at a desk with a pencil, before a single soul had a hope of ever catching such a ripple. He did the sum, out fell the wave, and then he had to sit and wait 100 years for the sky to say yes.
100 years, near enough, and he did not live to hear it said. Which is the thing about physics I find almost unbearable. One person pushing a pencil across a page in a quiet room, and thereby learning a true thing about the middle of the sky that no eye will confirm until long after he's gone. But now, careful, because I've handed you the pond, and the pond is about to tell you a lie.
The pond seems honest to me. What's it hiding?
You told me a ring races out across the water. So answer me one plain question, the way you'd answer a child. What is the ripple travelling in?
The water. Obviously. The pond simply is the water, and the ripple's a disturbance running through it. No water, no ripple. Same as a sound is nothing without the air to carry it. Same as, oh no, you've done this exact thing to me before, haven't you? I can feel the floorboards going soft under my chair.
I have, and I'm dragging you back to it on purpose, because you're about to make the same mistake one whole layer deeper. Years ago, in another course, on a night neither of us has forgotten, I made you hunt for the invisible sea.
Light. You had me searching high and low for the still, invisible ocean. Light was supposed to be waving in, the stuff that had to fill every corner of space, that simply must be there, or light made no sense. And then you stood there with your hands in your pockets and told me it wasn't there. There was no sea, light waves in nothing at all.
There was no sea. And the same lesson waits for you here, only harder. You want to know what the ripple in space is rippling through. And the answer is the thing it took Einstein himself the longest to swallow. The ripple is not travelling through space the way your pondering travels through water. The ripple is space. Space itself is the thing doing the waving.
Now, hold on, I don't even know how to hold that. A wave is a wiggle in some stuff. You taught me that yourself when it suited your argument. And now the stuff and the wiggle are the same thing. The dancer and the dance are one.
The dancer and the dance are one. That's the vertigo of it, and I want you dizzy. When a sound crosses this room, the air is one thing, and the wave is a pattern running through it. The air stays put, the pattern moves on and leaves it behind. But a gravitational wave has nothing behind it, nothing it's a pattern in.
Then what, in the name of anything, is actually moving? If there's no stuff to carry it, what wiggles?
The geometry wiggles, the very rulers and clocks that measure out the world. Those are what ripple. When the wave rolls through the room, it doesn't push the air about. It changes what a meter means, here, then here, then here, as it passes. The distance between two fixed points genuinely swells and shrinks. The measuring stick itself is the thing that waves.
So there's nothing left to hold a yardstick up against, because the yardstick's in on the conspiracy too. It's swelling and shrinking along with everything else.
The yardstick's in on it too, which is exactly why this was so nearly impossible to catch, and exactly why, when at last we did, it was the sweetest confirmation of the whole grand idea. But I'm running ahead. You've granted me that space-time can carry a wave, and that the wave is space itself in motion. Now I have to tell you what the wave actually does to you when it arrives. And here nearly everyone, clever and foolish alike, guesses wrong on the first try.
I do enjoy being told I'm about to be wrong. It's practically our love language. Set it up then. A ripple in space comes rolling toward me out of the dark. What does it do to me?
Forget yourself for a moment. You're too complicated a shape. Imagine instead floating out in the deep empty where nothing can nudge them, a ring of little beads. A circle of them, holding hands, a perfect round hoop, just hanging there, weightless, in the black. Now the ripple comes, straight at the ring, aimed at the middle of the circle, coming toward your own face if you were the bead at the very center. Watch what it does to the hoop.
It squashes it. It's a wave. It hits the ring, so it crushes the whole circle flat, like a boot coming down on a hoop in the grass.
Every last person says a version of that, and it's wrong in the most instructive way there is. It does not shove the beads toward you, and it does not shove them away. It doesn't crush the hoop flat. Watch closer. As it sweeps through, it reaches into the flat face of the circle and does two opposite things in the very same instant. It stretches the hoop tall, pulls the top bead and the bottom bead apart, up and down. And at that same moment, it pinches the hoop narrow, squeezing the left and right beads in toward the middle. Your round circle becomes an egg standing on its end, tall and slim.
All right, so it's an oval now, not a circle. It's stretched the one way and squeezed the other. Peculiar, but I can make my peace with an egg standing on its end.
Ah, but it won't hold still. Give it one more breath, and the wave swings the other way. The tall stretch lets go, and the ripple does the exact opposite. It pulls the left and right beads apart now, stretches the hoop out wide, and pinches the top and bottom in. The egg that stood on its end lies flat on its side, wide and squat.
So it went from a tall egg to a wide egg. And from the gleam in your eye, it doesn't have the decency to stop there either.
It never stops, so long as the wave keeps coming. Tall, then wide, then tall again, then wide again. The two directions forever swapping, one stretching at the precise instant the other squeezes, over and over, for as long as the ripple rolls through.
So the up and down and the side to side are always doing the exact opposite of one another. The moment one stretches, the other squeezes, and then a beat later, they trade jobs. Have I got that?
Always the opposite, never the same. And that is the fingerprint, the one thing in all the world that says a gravitational wave came through this spot, and nothing else in creation could have. Pick any direction across your body. When it stretches a little, the direction square across it, at a clean right angle, shortens by just as much, and a moment later the two of them swap. There's a stiff name for that pattern, which I'll give you once and ask you to throw away. A stretch married to a squeeze at right angles. Physicists call it a quadrupole. 4 poles. 4 petals of push and pull round a center. But throw the word away and keep the picture. A circle breathing into an egg and back. Tall, wide, tall, wide.
And if it were me floating there instead of the beads, if the ripple rolled clean through me, I'd be pulled tall and pinched narrow, then squat and stretched wide, over and over, the whole time it passed.
Over and over, every part of you at once. Your bones, your blood, the air in the room itself. Head to toe you'd lengthen, while shoulder to shoulder you'd draw in, and then the exact reverse, in perfect time, again and again. You would feel none of it, mind. It's far too gentle, and every ruler you might check yourself against is stretching right along with you, keeping the secret. But it happens to all of you, faithfully, as the wave goes by.
Now I want to say a thing, and tell me flatly if it's wrong, because it has the feel of a wrong thing. What you're describing sounds an awful lot like a sound wave, something squashing me and unsquashing me. The way a sound is really just the air bunching thick and thinning out. Is it that?
It is not, and I'm glad you reached for it, because knocking it down is how you truly own the picture. A sound wave, which way does it do its squashing?
Along the way it's going, I suppose. The air bunches up out in front, in the direction the sound's travelling, front to back. The squeeze runs forward, the same way the sound runs forward.
Front to back, along the line of travel. A shove, running forward. A completely different animal. Our gravitational wave comes straight at you, head on, and yet the stretching and squeezing happen entirely across your face. Side to side, up and down, at right angles to the way the wave moves, never along it.
So it never actually pushes me. It's coming right at me, barreling into my face, and it never shoves me backward.
Never once. It never crushes you front to back, never presses you a hair's breadth backward. It comes head on and it kneads you sideways, in the plane of your own face. It's not a shove and it's not a punch, it's a knead. Remember that word, a knead, not a shove, and you'll never again confuse this with a sound or with any ordinary wave you've met.
A knead? So if I stood facing the oncoming wave and held both hands up flat toward it, palms out, all the stretching and squeezing would happen right there in the flat of my palms, not pushing my hands back at me.
Right in the flat of your palms, each one going from round to a tall oval to a wide oval and back, and never once feeling a push toward you. You've got it. And here's something that falls straight out of that picture and answers a question you were already halfway to asking. Why does it take two black holes? Why couldn't one lonely star, sitting by itself, send out a ripple like this?
I was going to ask that, blast you. Why the pair? Why the whole whirling dance? Why couldn't one big heavy thing just sit there and throb, swell up and shrink down over and over, and shake the fabric that way?
Because a thing that merely throbs, swells bigger and shrinks smaller, evenly all over at once, like a single beating heart, sends out no wave at all. And a thing that only slides plainly back and forth in a straight line sends out no wave either.
Neither one, not the throbber and not the slider. Why on earth not? Surely something that big, moving that much, shakes something loose.
Because neither makes the telltale pattern. The stretch here and squeeze there, the tall married to the wide. A throb is the same in every direction at once, so nothing stretches while its crossways squeezes, and a straight slide is only a push, to and fro. To make the real pattern, the mass itself has to slosh in that lopsided, crosswise way. And do you know the one thing in the universe that naturally, gorgeously throws its weight around in a stretch one way, squeeze the other pattern?
Two things whirling round each other, a pair. Because at any instant the two of them are strung out along one line, that's the long direction, the stretch, and a quarter turn later they've swung round, and they're strung out along the other line, the crossways one. The heavy stuff is going tall, then wide, then tall, then wide. The dance is the pattern.
The dance is the pattern. Two heavy bodies swinging round each other trace out, with nothing but their own moving mass, the exact tall then wide shape the wave carries away. That's why it takes a pair, never a loner, and it's why the loudest source in all the sky is two black holes locked in a death spiral. The heaviest things there are, whirling in the tightest, fastest circle there is, stirring the stiff fabric in precisely the pattern that flings a ripple off across the universe.
All right, that's beautiful, and I'll say so, but now you have to pay the debt you ran up at the top of the night because I've been keeping the account. This is the most violent event you can imagine. Two black holes, the heaviest things in creation, whirling as hard as anything can. And the very best it manages to do to me when its scream arrives is a wiggle smaller than a piece of an atom. Why is it so pathetically, insultingly small?
And there it is, the true heart of the night. Not how enormous the source is, but how stubborn the fabric is. Let me answer it by reaching back to an equation we met a few evenings ago, the famous two-sided one. Do you remember its shape?
Matter on the one side, telling spacetime how it must curve, and the shape of spacetime on the other, turning round and telling the matter how it must move. The two-way handshake, the thing that bites its own tail.
The very one. And do you remember what I told you about how hard it is for the matter side to move the geometry side even a little?
You said it takes an enormous heap of stuff to bend spacetime by a tiny bit. That's why we don't feel the whole Earth curving the space beneath our feet as anything dramatic. It takes a whole planet just to make us drift gently off the edge of a chair. Space doesn't bend easily, it resists.
It resists ferociously. So here's the single word I want you to carry home tonight and keep. Space-time is stiff. Not soft, not slack, not a loose bedsheet you can ripple with a breath. It's the stiffest, tautest, most unyielding thing there is. Stiffer than steel, stiffer than diamond, by a factor with no comparison you could hold. And a stiff thing barely moves, however hard you strike it.
Give me the version I can feel in my own hands. What does stiff feel like in a thing I could hold?
Pluck a slack rubber band, and it flaps all over the place, soft and loud and lazy. Now pluck a steel wire, strung tight as the tightest string on a piano. It barely stirs. You have to strike it savagely hard just to wring the faintest note out of it, because it's stiff, and a stiff thing hoards its stillness.
So spacetime is the tightest string in all of existence. And to get any wiggle out of it, any wiggle at all, however small, you'd have to strike it with something monstrous.
With something monstrous. Which is exactly why the rest of the universe is silent to us on this. Shall I tell you a small secret about your own kitchen? A pair of dumbbells, spun round on your breakfast table, makes gravitational waves. Truly, the equation doesn't make exceptions. Ripples of pure space-time rolling silently off your morning table this very moment.
And I feel exactly nothing sitting there eating my toast, so I take it these particular ripples of mine are on the modest side.
So unspeakably faint that no instrument that could ever be built would feel them across the whole age of the cosmos. The Earth, swinging its great mass round the Sun, makes them too, and even those are beyond any hope of catching. To make a single ripple large enough to cross 1 billion years and still be caught, trembling at the far end, you need the most violent event the universe has in its cupboard.
The two black holes, pouring the mass of whole suns into the crash.
Into one brief scream of pure, bent space-time in the last breath before they touch. And let me give you the size of that scream because it beggars belief. For a fraction of a second, those two black holes poured out more sheer power, all of it as ripples in the shape of space, than every star in every galaxy in the whole visible universe was giving off as light, all of them added together at that same moment. The most blinding outpouring of energy since the universe began, and not a single flicker of it was light. And even that, the single most violent thing there is, arrives here as a shiver smaller than the heart of one atom. Not because the event was small, because the fabric is stiff.
So the smallness was never a sign the wave is feeble. The smallness is a measure of how strong space is. The wave is tiny because it crossed the toughest, tightest medium there could ever be. And even a cosmic catastrophe barely dented the thing.
You've turned it round exactly the right way, and it's the turn most people never make. The tininess is not the weakness of the wave, it is the strength of space. Every feeble little tremor we catch is a quiet monument to how impossibly hard it is to shake the ground of the world even a little. And be glad of that stiffness, mind. It is the very same stiffness that holds the planets steady in their orbits for billions of years, and holds the shape of the world together under your feet, and does not go rippling wildly every time a lorry rolls past. A slack universe would be a nightmare to live in. We only notice the stiffness at all because, once in a great while, something violent enough comes along to make even the tightest string in creation hum.
I don't think I'll hear the word small the same way again. All right, one last thing about that ripple while it's still crossing the dark toward us. How fast does the thing travel?
You told me yourself at the very top of the night. The speed of light.
It raced away from the collision at the speed of light and took 1 billion years only because the collision was 1 billion light years off. But why the speed of light exactly? Light's a wholly different thing from a ripple in space. Why should a wave in the fabric keep perfect pace with a plain beam of light?
Because at bottom, they're the same kind of news, though never the same thing, and I'll not have you muddling them. A wave of light is a ripple of the electric and magnetic fields riding upon the fabric. A gravitational wave is a ripple of the fabric itself. Two different animals, but they share one deep property. Neither carries any mass, and anything in this universe that carries no mass travels at that one speed. The cosmic limit, the pace light happens to travel at, and the pace gravity's news travels at too. Not a hair faster, not a hair slower.
So gravity has no secret shortcut. It can't outrun its own light. The news of a thing and the light of a thing arrive together.
No shortcut anywhere. If the sun were, this instant, to simply blink out, the Earth would not know it, would not feel its orbit go slack and begin to drift. For the same handful of minutes it takes the last sunlight to reach us. The news of the missing sun and its last light would come knocking at the same moment, hand in hand. Gravity travels at the one speed, the same as light.
The one speed. For everything in creation that weighs nothing. There's a tidiness to that I hadn't seen coming. So, Einstein predicted it all at his desk. The wave is space itself. It needs you sideways. It's faint only because space is stiff, and it flies at the speed of light. That all sounds settled and finished. So why do I have this sinking feeling you're about to tell me it was anything but?
Because it was anything but. And here's the part of the story I love the most, the part that makes even Einstein human and a little lost. He wrote the ripples down, out of his own equation, and then, for years afterward, on and off, for much of the rest of his life, he wasn't sure he believed in them.
He doubted his own prediction, the wave that fell straight out of his own famous equation, in his own hand. How does a man do that?
He kept wondering, right to the end of his working life, whether the ripples were real at all, or only a kind of mirage shimmering in the mathematics.
A mirage in the mathematics. What can that even mean? How can a thing sit right there inside your own equation and also not be real?
It means this, and it's subtler than it sounds. The wave is a wiggle in the rulers and clocks, in the very grid you lay over the world to say where things are and when. And that carries a nagging worry. What if the wiggle is only in your description? What if you drew your map of space in a slightly wobbly way, and the wobble is in the map, not in the territory it describes?
A crease in the graph paper, not a real mountain out there in the world. And that's genuinely unsettling, because everything you've shown me tonight, the ring of beads, the tall then wide, I've been picturing as a real thing happening to real beads. And you're telling me that for years, the sharpest minds going couldn't be certain it was more than a smudge on the chart.
For years they couldn't. And do you know how it was finally settled? The plain little argument that put the doubt to rest. Simple enough to follow right now in your chair. Ask yourself one question about the ripple. Can it do work? Can it push something, warm something, move something that pushes back?
If it's only a smudge on a diagram, then no, a wrinkle in graph paper can't warm a teaspoon. But if the ripple can make something happen out in the world, make a real object hotter, do an honest job, then it has to be real. A smudge can't do a job, only a real thing carries energy, and only energy can do work.
That's exactly the blade that cut the knot. Picture two beads threaded loosely on a rod, free to slide, but with a little friction so they drag as they move. Now let the ripple pass through.
And the beads are forced to slide back and forth along the rod because the wave stretches and squeezes the space between them. The gap keeps swelling and shrinking, so the beads have no choice but to slide to keep up.
And beads sliding against friction.
Make heat. They rub and the rod gets warm. Oh, and a warm rod is a real thing. You can't stand there and argue a genuinely warm rod is only a smudge on somebody's diagram.
You cannot. The ripple delivered real energy. You could, in bare principle, cook your supper on it, if only it weren't so absurdly faint. And a wrinkle in a diagram cannot warm a rod. So the wave is not a smudge. It's out there in the world, carrying real energy across the dark at the speed of light. Energy the two black holes paid out of their own substance as they fell together.
So the doubt that troubled Einstein for half his life was answered, in the end, by two little beads on a rod, and the plain fact that the thing can warm them. The wave can heat a rod, therefore the wave is a thing. That's an argument I could have followed at my kitchen table, and it laid to rest a question that unsettled the man who dreamt the whole theory up. I find that somehow enormously comforting.
It comforts me too. Physics at its most honest. A great mind unsure of his own creation for years, and the doubt dissolved not by some blaze of cleverness, but by a plain question, plainly asked. But now, my friend, now we come to the mountain. It's one thing to prove on paper that the wave is real and carries energy. It's another thing entirely to actually catch one. And I've been dreading this part, because I have to make you feel in your bones how nearly impossible it was.
The wave stretches me by less than a single piece of an atom. So how, in the name of anything, do you build a machine that could notice a stretch that small? Every ruler I could hold up is itself made of atoms. And the stretch you're chasing is far smaller than the atoms in the ruler doing the measuring.
You've walked straight into the exact stone wall the whole problem crashes against, and named it better than most books do. Your ruler is made of atoms, and the thing you're measuring is smaller than those atoms. So you cannot use a ruler. You cannot use any solid thing at all.
Then what's left? What can you measure a length with, if not a solid stick laid alongside it? That's what measuring is.
What's the finest, steadiest, most trustworthy thing there is? The one that never wobbles, never wears down, never bends a hair with the weather.
Light. It's always light with you, in the end. Everything in this course comes back around to light.
It always comes back to light. And here's how the thing was actually done. One of the most beautiful machines human beings have ever built. I'll not tell you its name, nor where it sits, only what it does. Imagine an enormous letter L laid flat on the ground, and each arm of it stretching away from the corner for miles. Down each arm you send a beam of light, racing to a mirror at the far end and racing back. And you compare the two beams so exquisitely finely that if one arm grows even a single hair longer than its neighbor, the light tells on it. To hold a thing that still, you must hush the whole world out of it. Hang the mirrors from the finest threads so no footstep, no distant sea, No rumble of the Earth's own guts can jostle them. Chill it, still it, and bounce the light up and down the arms hundreds of times over to sharpen the reckoning. It is less a machine than a held breath, miles long, waiting.
Two arms at a right angle square across from each other. Wait. That's the shape of the wave. That's the tall, then wide. One arm plays the up and down direction, the other plays the side to side, and so when the ripple comes rolling through,
it stretches the one arm at the very instant it squeezes the other. Exactly the quadrupole, one direction lengthening as the direction square across it shortens. The whole machine is built, deliberately, in the shape of the wave's own fingerprint.
So the wave does the work for you, makes one arm grow long while it makes the other shrink short at the same moment. It's practically designed to be caught by an L.
An L is the one perfect trap for it in all the world. As the ripple rolls through, one arm grows a touch longer and the other shrinks a touch shorter, and the light running up and down them falls just barely out of step. Then a breath later, the arms swap, and it falls out of step the other way. And light is patient enough and fine enough to catch even that.
And the difference it's catching, over two arms that are each miles long, is still smaller than a single piece of an atom.
Smaller than a single piece of an atom. Over arms as long as a tall mountain is high, the passing wave changes the length by less than the width of the tiny core at the heart of one atom. It is, and I'm not reaching for effect, like measuring the whole span between here and the nearest star, and being flatly certain of a change no wider than a human hair.
That can't be real. That isn't measurement, that's sorcery with extra steps. Nobody can be sure of a thing that small.
It's the finest measurement our species has ever made. Two of the most sensitive instruments ever built by human hands, tuned to catch a whisper of a whisper of a whisper. And for decades they listened and heard nothing, and were made finer and listened again.
Why two of them? Why build the impossible thing twice?
Because a signal that faint hides down inside every kind of noise. A heavy truck on a far-off road, a wave breaking on a distant shore, the endless trembling of the atoms in the machine's own bones. But a real ripple from the sky sweeps across the whole Earth at once. It passes clean through both machines, set far apart, at nearly the same instant. A passing truck rattles only one. So you build two, hundreds of miles apart, and believe only what the both of them feel together. And here's the loveliest part. When the real ripple finally came, it struck the one machine, and then the other a few thousandths of a second later. Exactly the sliver of time light itself needs to run across the gap between them. Which means the wave had swept over the whole Earth at the speed of light, just as Einstein swore at his desk that it must. And the two machines, feeling it one after the other, measured that speed between them without anyone even setting out to.
Two witnesses to the same tremor, far enough apart that no local accident could ever fool them both. And then, one ordinary morning,
after all the decades of hushing the noise and all the waiting and all the doubt running back to Einstein at his desk, the ripple came in. And here's where the whole night pays off, so let me tell it slowly. Remember what the wave carries in it.
the pattern of the whirling pair that made it, the tall then wide of the dance printed into the ripple.
Just so. Now, as two black holes spiral inward, closer and closer, what happens to their dance? They fall closer together, and the closer they fall,
the faster they whirl, round and round, faster and faster, tighter and tighter, in the last moments before they touch and become one.
and the wave faithfully carries the whirl out into the dark. So if the whirl is speeding up,
Then the ripple coming off it must be speeding up too. The stretch and squeeze has to arrive faster and faster and faster still.
Quicker and quicker and quicker. A wave whose whole rhythm rises, climbing, accelerating, right up to the single instant of the crash. And here's the thing that raises the hair on my arms every time. That rising rhythm, the pace of the stretch and squeeze in those final fractions of a second, happens, by pure blind luck, to fall right within the range of things a human ear can hear.
So you can, turn the thing into an actual sound? A sound a person could listen to?
You take the wiggle the machine felt, the swelling and shrinking of those mile-long arms, and turn it, faithfully, note for note, into a sound you can play out loud in a quiet room. And when you play the shape of space-time out loud, you hear a single tone that starts low and slides upward. Rising and rising, growing louder and faster and higher, right up to a sudden peak.
And that sound has a name, doesn't it? I can hear you saving one up, like the last sweet in the tin.
A chirp, like a bird calling. A rising whoop, climbing and climbing, ending in one bright cry at the top.
A chirp. The last fraction of a second of two black holes falling headlong into each other. 1 billion years old, 1 billion light years away. The most violent thing in creation reaches us as a small, rising bird cry. I haven't got anything funny to say about that. It's one of the most beautiful things I've ever heard anyone describe.
And it doesn't even end on the chirp. At the very peak of that rising cry, the two become one. The black holes merge, and that newborn thing is lopsided, misshapen, still shuddering from the violence of its making. And then it settles.
And as it settles down, it rings. There it is. That's the bell. The very bell you promised me at the end of last time and made me wait a whole episode for.
That is the bell I promised you. The newborn black hole shivers itself smooth, and as it settles into its final, still round shape, it rings. One last dying set of wobbles, quivering out into space and fading slowly to nothing. First the rising chirp, then the ring down. A rising cry, and then a single bell, tolling once and dying to silence. And a bell tells you things, if you have the ear for it. The pitch of the ring, and how quickly it fades, whispered to us how heavy the new black hole was, and how fast it was spinning, and confirmed there was truly just the one of them now, where an instant before there had been two. We read all that off the fading toll, the way you'd know the size of a bell from across a valley by its note alone. That is the sound of two black holes becoming one, and we caught the whole of it.
A rising cry, and then a bell fading out into the dark. And here I have to be careful because you've trained me for years to be careful. That isn't really a sound, is it? There's no air out there between the stars for a sound to travel through. Black holes don't actually make a noise.
You've been trained well and caught the one thing that matters most. No, and this distinction is worth everything. Nothing out there made a sound. There's no air anywhere between the stars to carry one.
So where did the sound come from? We didn't simply imagine it, and you played it for the whole world.
What crossed the billion years of dark was the ripple in the fabric, the silent stretch and squeeze in the rulers themselves. And what we did, here at the far end, was take that silent shiver and translate it, faithfully, into a tone we could play through the air of a room. The universe made no noise. We made the noise out of the trembling of space. A true translation, but ours, not the sky's.
So it's a translation. From a language of stretched and squeezed distances, which our ears can't hear, into a language of tones in the air, which they can.
Exactly that. But the rhythm is entirely real. The rising, the quickening, the peak, the single dying ring. Every bit of that came in from the sky. We didn't invent the tune. We only, at long last, gave it a voice it never had in a billion years of travelling.
We gave it a voice. And now I want to understand what we actually got out of all this, beyond the goosebumps, which are considerable. We already study the sky with 100 kinds of telescope, and we've been staring up for thousands of years. So what does a shiver in the fabric give us that all that patient looking never could?
It gives us a wholly new sense. And I mean that nearly literally. Every single thing our species has learned about the universe beyond the Earth, from the first shepherd who lay back and looked up, to the grandest telescope ever floated above the air. Every scrap of it we learned from light.
Every colour of it, mind, the light our eyes can catch, and the light they can't, beyond the red, beyond the violet, but always, always some kind of light.
Always some kind of light. For the whole of human history, we've had one sense trained on the sky. We have watched it. And the trouble with a watcher is that a watcher can be blinded.
Blinded how? Light seems to come at us from everywhere you look.
Light gets blocked, soaked up by dust, scattered by gas, swallowed whole by anything solid in its path. And here's the cruelest part. The most violent, most interesting events in the universe, the black holes themselves, give off almost no light at all.
So the one thing you'd most love to watch is the very thing that hides from every eye you own. You can't watch a black hole. There's nothing there to watch. It's the one great drama in the sky that light itself can't report on.
Light can't report on it, but the fabric can. The wave in space-time isn't blocked by anything. It sails straight through dust and gas and stars and whole planets, unstopped, precisely because it isn't a thing moving through space that space could get in the way of. It is space, flexing. So it brings us news, clean and undimmed, from exactly the places light can never escape. Think what that means. Those two black holes, we could never once have seen them, not with any eye or any telescope ever built, because they gave off no light to see. And yet we know they were there. We weighed them, we counted them, we watched them fall together and become one. All of it, every fact, read off nothing but the song they sang into the fabric as they died.
So for the whole of our history, we've been watching the universe as a silent film, beautiful and utterly soundless. And now, at last,
And now, for the first time, we've caught the soundtrack. We've grown a new sense. Not a sharper eye, but a wholly new organ, one that feels the shudder of the ground beneath everything instead of catching the light off its surface. A species that was sure it had found all its senses long ago has just now, in our own lifetime, quietly grown itself another. And the first thing that new sense ever heard was two black holes falling headlong into each other 1 billion years ago on the far side of the dark.
a new sense. After all this time, after thousands of years of only ever looking, that stirs a feeling I don't quite have a name for. Some cousin of standing alone at the edge of the sea at night and hearing it move. We spent our whole existence with our eyes open and our ears, it turns out, closed. And the universe was making it sound the whole time, and we simply couldn't hear it.
The whole entire time. Every collision of every pair of black holes since the beginning, every ring of every bell out there in the dark, all of it washing silently over the earth, passing clean through every one of us, forever. And we never felt a thing, only because we hadn't grown the sense to feel it with. Now we have. That morning I opened the night with, right at the very top, that is what it truly was. Not the discovery of some fact, the opening of an ear.
And now that the ear is open, what else is out there, waiting, that we've been deaf to all this time?
Whole choirs of it. Not black holes alone, dead stars heavier than the sun and smaller than a city, crashing together in a flash bright enough to forge gold, and pairs of them circling for an age before the end. And I've no doubt, tremors whose shape we haven't even the wit to guess at yet. We have caught the first few notes of a music that has been playing, unheard, since long before there was anyone alive to hear it. And we are only just now, fumbling and amazed, learning how to listen.
So here's where I brace myself, because I know your habits far too well. You're about to tell me all of this is the exotic far edge of everything, a billion light years off, the most violent event there is, a machine miles long to catch a shiver smaller than an atom, the furthest thing imaginable from my ordinary Tuesday. So please, tell me it's not about to turn out to be sitting in my coat pocket.
It is sitting in your coat pocket, right now, this minute. And that's exactly where I want to leave you tonight, with the ground pulled out from under the word exotic. Everything we did this evening rests on one idea, the idea this whole course has been about. That gravity is not a force reaching across space and tugging. It is space-time itself, bending.
I've got that one in my very bones by now, 9 long evenings of it drummed in.
Then here's the final twist of the knife. The thing space-time bends the most, close to home, down here where you live, is not space at all. It's time. Time itself runs at different rates in different places, depending only on how deep in gravity you sit. We brushed against that years ago, and I made you a promise about it.
You did. Clocks that run at different speeds, depending only on where they sit. I filed the whole business under unsettling things George will one day make me regret asking about.
And that day is next time. Because there are machines wheeling silently over your head this minute. Satellites riding high up, where the Earth's gravity is a touch gentler than down here on the ground. And up there, where the fabric is bent a little less than at your feet, time runs at a different rate than it runs for you. Faster, in fact. And those satellites carry the most exquisite clocks, and their whole job is to tell the little machine in your pocket exactly where you stand on the face of the Earth. But they can only do that if their clocks up there and your clock down here agree on what a single second is. And they do not, because time up there genuinely, measurably runs at a different pace than time down here.
So the little machine that tells me which street corner I'm on leans its whole weight on clocks in the sky that don't keep the same time I do. And if it just ignored all that, pretended time ran the same everywhere, up there and down here alike?
Then, within a single day, it would walk you calmly into the wrong street, and then the wrong town, drifting you further off, mile by mile, with every hour, until it was worse than no help at all. The humble thing that finds you a warm cafe in a city you've never set foot in is quietly correcting itself every second, for the plain fact that time runs slower down at your feet than up over your head. It would fail you utterly, within a day, if it ever once ignored Einstein. The same bending that rang a bell across a billion years of dark is running, right now, in the small, warm thing in your pocket, keeping you from ever getting lost on the way home.
So it was never truly exotic at all, was it? The shudder from those 2 dead black holes and the little glowing arrow on my phone are the very same physics underneath, space-time bending, and bending time most of all. Tonight I felt the whole universe grow itself a brand new ear, and I heard 2 long dead stars fall headlong into one another from the far side of forever. And now you're telling me the same idea is the quiet reason I can always find my way back home. I honestly can't say which is stranger, the great cosmic one, or the plain fact that it's been riding in my coat pocket the whole time, keeping me honest, and I never once thought to thank it. So, next time then, the clocks that refuse to agree, and just why the one held over my head is forever racing ahead of the one down at my feet. I'll bring my own watch along. I've a strong feeling I'm about to stop trusting it entirely.